Hello student, hi, good evening. So today we are going to we are going to discuss about the topic by the name of gain margin and phase margin. Okay, so gain margin. So because the question that the next question, that is question number 71, that is related to gain margin. Okay, so gain margin of the system. So before solving the question, we are going to the topics of discussion, that is about gain margin. What is gain margin? So this is my topic. So today's topic is gain margin. Gain margin. Gain margin. Okay. So gain margin. So is it visible? Yes. So today we are going to discuss about gain margin. What is gain margin? Okay. So let us write somewhat bigger. Okay. So this is what gain margin. Gain margin. Gain margin. Okay. So today we are going to discuss about gain margin. So what is exactly gain margin? So gain margin of the system. Gain margin of the system. So if we have some system, okay, so open loop system. So what is actually the gain margin? Gain margin is nothing but gain margin is what? It is like say for example, if I will say here for example, okay, for example, so there is one like competition, okay, so like there is one exam. Yes, there is one exam, and in this exam there is a what 30 marks. If let's say 30 marks, that is what eligibility criteria. So this is 30 marks is my eligibility criteria. Eligibility criteria. Okay, this is my eligibility criteria for this exam. Okay, so one particular exam is there. So for that, this is my passing marks. Okay, so passing marks. These are my passing marks. Passing marks. Okay, so now just but you got what you got. You got how many marks? You got just how much? You got 28 marks. Yes, 28. You got 28 marks out of 30. Okay, 28 out of let's say 100. Okay, but passing marks is 30. Passing marks is 30. So you got 28. How many marks you are left? Okay, so from this 30. So how much far away you are from this 30? 2 marks. Yes, 2 marks left. Yes, 2 marks. Okay, so what is this 2 marks is nothing but gain margin. Gain margin. This is your gain margin. Yes, this is what your gain margin. So there is a particular exam. Okay, so eligibility criteria or passing marks for that is 30 marks, but you got 28 marks. How far away you are from your passing marks? You are just far away of 2 marks, and these 2 marks is nothing but gain margin. This is what gain margin. Okay, so gain margin of about your particular exam. So to qualify this exam, so it required 30 marks, but you got 28 marks, but you are 2 marks, okay, away from this passing marks. Okay, so that means what? If you will achieve these 2 marks, and you will reach to what? You will reach to eligibility criteria. Okay, so this is what words of stability. At the words of stability, and you will get qualified. Okay, so with this gain margin. So this is only what about gain margin. Okay, so something that you want to achieve, something that you want to achieve. So there is something, what there is a eligibility criteria. Everywhere there is eligibility criteria. First of all, you have to qualify that. Qualifying the eligibility criteria for something. So that is nothing but gain margin. Yes, that is nothing but gain margin. How much far away you are from your qualifying marks for any, for any exam or other things that required to become eligible. Okay, so that is all about what. So this is nothing but gain margin. Okay, so in lay language. Okay, so layman language, I want to say that this. Okay, so that is what, that is just a means in layman language. Okay, so now just you see technical language. What is this gain margin? So gain margin is nothing but it is a factor. Okay, so gain margin is a factor okay, by which the transfer function of the open loop system. Okay, so open loop system is multiplied. Okay, so multiplied so that the closed loop system will become stable. So you can write also like this. So gain margin is what? Gain margin gain margin gain margin is a factor. Yes, gain margin is a factor. Gain margin is a factor. Gain margin is a factor by which by which open loop system, open loop transfer function open loop transfer function open loop transfer function is multiplied multiplied open loop transfer function is multiplied so that so that closed loop system closed loop system become become marginally marginally stable marginally stable. Okay, so this is nothing but gain margin. What is gain margin? Gain margin is just a factor by which the open loop transfer function is multiplied so that the closed loop system become marginally stable. Okay, so this is uh, like this is here. This is my words of stability boundary. Yes, this is the boundary of words of stability, means marginal stability. But you are here. Okay, you are here. Okay, how much far away you are. So this is what words of stability here. Once you will reach here, you will, yeah, you will achieve your what goal. So let's say you have what, you have one ultimate goal, so that you want to achieve. Okay, so you have reached from this path and you have reached up to this path. Okay, so up to this path, how much distance you are away from your ultimate goal. So let's say this is what k distance. Yes, this k distance, this k distance, between k distance is nothing but your gain margin. And this final boundary is what your eligibility criteria, so that it will qualify that you have achieved your ultimate goal, your ultimate goal, so where you want to see yourself, okay, but you have reached up to this, and this is what, this is key distance far away from your ultimate goal, and this k distance is nothing but gain margin, okay. So anything that you want to achieve in your life, okay, so in your life, so definitely there is a something eligibility criteria for that, you have to qualify that criteria, okay, so to become how much far away you are from your eligibility criteria, so that is nothing but gain margin. In simple way, if you say how much far away you are from your eligibility criteria is nothing more than that of a gain margin. What? Gain margin. So similarly, if you have one open loop system, you have system, okay, open loop system. If you will transfer, okay, so open loop system, you want to make that open loop system closed loop system, okay, closed loop system. Then you want to see whether my closed loop system is stable or not stable. For that, what you will do, just you will multiply one factor, just you will multiply one factor from what, with what, with the transfer function of open loop system, open loop transfer function, okay, so that your closed loop system will become marginally stable. So this is about gain margin. So now see here, if I have what, if I will take one open loop system, that is my g of s, okay. So let's say I'm going to what, select one open loop system, that is g of s is equal to what, g of s is equal to, g of s is equal to s plus 1, s plus 1 into s plus 2, okay. So I have this what, open loop system, this is my open loop system, okay. So this is my open loop system that I have selected, okay. So this is my input r of s, and this is my g of s, this is my g of s, okay. So now, and this is connected, I am connected this to unity feedback system, and this is what, c of s, this is c of s, okay. So this is my c of s, this is my open loop system, open loop system. Now in closed loop system, I want to make this closed loop system stable. Then what I should do, so this is my open loop system, okay. So similarly, as per definition, what the open loop, so the gain margin, it is a factor, what factor, let's say, so this factor is nothing but k factor, what, k factor. So first, let me remove this first, okay. So this is definition about this gain margin is what, it is a factor by which we are multiplying what, the open loop transfer function, okay, so that the closed loop system will become marginally stable. So let's see here. How to understand this now mathematically. So if you see what we have, what we have, one open loop system that I have chosen, like 1 by s into what, s into s plus 1, s plus 1 into s plus 2, s plus 2, okay. So this is my open loop system that have I have selected. Okay, so now this is what, this is connected like this. So this is my input R of S, and this is what, this is my open loop system G of S. Now I am going to connect this through unity feedback system to make this closed loop system. Now how I can say that my closed loop system is marginally stable. Then for this, what I should do? So what I should do? So I will multiply one factor, okay, one constant factor. That factor will be my gain margin, okay, gain margin. So this is as per definition, multiplying this factor with what, multiplying this what, this transfer function of open loop system with constant factor k. So constant factor k. So I am multiplying this with constant factor k. Okay, so k into g of s h of s, g of s h of s. Okay, so where this k into g of s h of s, where h of s is nothing but unity. Okay, unity feedback. So I am multiplying this with this. Okay, so now when I will multiply this k into g of s h of s, okay, k into g of s h of s. So like this is what, this is now new factor, new what, new system with what, with constant factor k, k into g of s, k into g of s, and this is my unity feedback system. So let's see, this is my unity feedback system. So c of s, c of s, and this is my r of s. Yes, r of s. Now what I am doing, just writing what, characteristic equation. As we know very well, what is the deciding factor for stability of the system is nothing but root of the characteristic equation. So this is my characteristic equation, 1 plus g of s, g of s into h of s, g of s into h of s is equal to what, 0, is equal to 0. So now see here, 1 plus g of s into h of s is nothing but k. k divided by s into s plus 1, 1 into s plus 2, s plus 2 is equal to what, 0. Yes, is equal to 0, which implies that s into s plus 1, s plus 1, s plus 2, s plus 2 plus k is equal to what, 0, is equal to 0. So now see, just multiply this. Okay, so open this, s, this become s cube plus 3 s square, 3s square plus 2s plus 2s plus k is equal to what, 0, is equal to 0. Now, if you see by RH criteria, by Routh-Hurwitz's criteria, so which, okay, so Routh-Hurwitz's criteria, from there you can find the stability, marginals, what gain margin, okay, you can find the marginal stability of the system by using RH criteria. As we know, from this, the internal product must be equal to, external product. So internal product must be equal to external product. Okay, so that closed loop system will become marginally stable. Okay, so this is what, this is actually, this is the condition. Okay, this is the condition which is given by RH criteria. Why RH criteria? When we write the RH table, okay, so RH table, so let's see here, I am writing this one. So just again I want to remove this here. Okay, so this is what, this is the condition. If you see here, s cube plus 3s square plus 3s square plus 2s plus k, 2s plus k is equal to what, 0. Okay, so this is my internal product and this is my external product. So this is internal product and this is my external product. Okay, so when both of these product will become equal, okay, so then we can see that the system, closed loop system is what, stable, means marginally stable. Okay, so if we see marginally stable, this is what, c, 6 equal to, this is the internal product, 6 equal to what, k, is equal to k. So this implies what, this is why, this is what, marginal stability. This is what the system is marginally stable. So gain margin, if you see for this gain margin is nothing but, k. K is equal to what, 6. 6 means what we can say that we can say that if we multiply the transfer function of open loop system with 6, then over closed loop system will become marginally stable. Now we have what we have found that as we have taken this g of s is equal to how much? G of s is equal to 1 by s into s plus 1 into s plus 2. Okay, so now if I will multiply this transfer function of what open loop system with what 6, then my closed loop system, what is closed loop system? G of s over 1 plus g of s into h of s. My closed loop system will become stable. So this is my closed loop system. What? G of s into h of s. So this is what negative positive. So this is r of s. This is my open loop system. Yes. So this is my open loop system and this is my closed loop system. Yes. So this is my closed loop system, this is my open loop system. If I will multiply this open loop transfer function system with 6, then this closed loop system, this my closed loop system will become stable. So here I am just multiplying it with 6. Okay, 6. This means this closed loop system will become stable if I will multiply this by what? 6. This by 6. What is this 6? This 6 is nothing but gain margin. What? Gain margin. That means what I'm just qualifying my what boundary condition of what? Boundary condition of marginal stability or words of stability. Yes, words of stability. So this is the gain margin. Okay, so or in dB you can say that gain margin is equal to this is okay. So this is my gain value of k. Okay, so this is what k value. How much k value should be there so that system become marginally stable? Okay, if we multiply this with 6 and it become marginally stable system. But the k value, but this is just marginal stability value of what? K value is equal to 6. Okay, if I will take the k value is equal to 6, then my closed loop system will become marginally stable. But the gain margin is what? Gain margin is reciprocal of this. Gain margin is reciprocal of this. Reciprocal of this, and this is 1 by k. This is 1 by k, and if I will take this in dB, it become minus 20 log what? K. Minus 20 log k. Yes, minus 20 log. Yes, so this is my gain margin. Yes, so just wait. 20 log 1 by k minus 20 log 1 by k. Sorry. Okay, so this is my gain margin. This is my gain margin. Okay, so gain margin. So this is what? K. Yes, so that if I will multiply with k this system, uh, my closed loop system will become marginally stable, and this is what? K marginal value. Okay, so that is. Yes, so actually yes, this is minus 20 and it will become 20 log k. Yes, 20 log k, and this is my gain margin. Yes, gain margin. So it will okay, so up to this is okay. So gain margin. So now we will see this with the help of. Okay, so this is what any system, if you will take any open loop system. Okay, so any open loop system, first multiply that system with what? K. With k, like this. K Okay, so if we have taken one like feedback system g of s, then this is k g of s h of s, and add this with 1 is equal to what, 0. So this is what your characteristic equation g of s into h of s. Okay, g of s into h of s. So this is what 1 plus k, 1 plus k. Then solve this what characteristic equation and see the order of this characteristic equation. Then after that, if you want to find the root of this characteristic equation with the help of RH criteria. Okay, from there you can find what this k factor. Okay, k factor. So that k is nothing but marginal, means uh, k marginal. So that is your k marginal. So at that value of k, your system will become marginally stable. Okay, marginally stable. So this is marginal stability. This is what k margin, and but the gain margin for this is 1 by k. Gain margin. Okay, gain margin for this, if you will see, this is what, this is in linear. This is in linear, and but this is in dB. This is in dB. Okay. Hmm. So if you see now, so this is all about. Okay, if you see here in this polar plot, so this is so okay, so we will see this polar plot again separately. Okay, first of all you should know about this gain margin, and after that if you will see for phase margin. Okay, if I will say for phase margin, what is phase margin? Phase margin of the system. So this is all about gain margin. Okay, so phase margin we will see with what, with the Nyquist plot. Okay, so now we are going to take one Nyquist plot. Okay, here we will see both gain margin and phase margin simultaneously. Okay, so this is my phase margin, phase margin. This is my phase margin. Now, I am taking some some system. Okay, so let us say this is my G1 of S. G1 of S is equal to is equal to G1 of S is equal to, let's say this is my 2 divided by S into S plus 1 into S plus 2, S plus 2, and here I am taking next G2 of S is equal to, let's say I am taking this 12 divided by S into S plus 1 into S plus 2. Yes, and I am taking third one G3 of S is equal to 24 divided by S into S plus 1 into S plus 2. Okay, so for understanding purpose, there is a variation of what, this k value. Okay, so this is just a variation in the k value. Yes, now let's say if I will see this g1 of j omega, g2 of j omega, g3 of j omega, if I will see for this my what, magnitude. Yes, magnitude. And what is magnitude, if you will see 2 by omega, 2 by omega into omega square plus 1, omega square plus 1, and this is what, omega square plus 4, and omega square plus 4. And if you see similarly for this is what, magnitude. So and angle phi is equal to what, minus 90 degree. Okay, so minus tan inverse tan inverse omega minus tan inverse. So this angle is same for all. Yes, so if you see for this is, let's say this is my m1 and this is my m2, m2 is just here 12, and omega square root of omega square plus 1 square root of omega square plus 4, and here m3 is equal to 24. 24 divided by omega into omega square plus 1 into square root of omega square plus 4. Yes, and if you see angle phi, this is equal to what? Angle phi 1 is equal to angle phi 2 is equal to angle phi 3. So these are equal, and this is nothing but minus 90 degree minus tan inverse omega omega minus tan inverse to omega. Yes, these angle are these angle for all these three system, the angle is same. Okay, so but there is only difference in magnitude. Okay, difference in magnitude, but angle is same, angle is similar. So now if you will see, now we are going to draw what? Nyquist plot for this on GHS plane, in GHS plane. Okay, so as we know very well, Nyquist plot, polar plot, that both these plot are drawn on GH of S plane, whereas root locus that is drawn on S plane. Okay, so here we are drawing the Nyquist plot, and with the help of Nyquist plot and with the help of Nyquist plot, we are going to understand about gain margin and phase margin. Okay, so let's see. If you see here first, first m1 at omega is equal to 0 and omega is equal to infinity. Okay, so let's see this value first for for what? For g1 of omega, g2 of omega. Okay, so here omega is equal to infinity. Here we will see first m1, and then we will see m2, and then we will see m3 magnitude. Okay, and here we will see angle phi, which is same, which is similar for all these three system. Okay, so let me. Okay, so this is what? This is omega. Omega is equal to infinite. Okay, if you will see here, just this is m1. If you will see, this is 2 by 0, infinity. Yes, infinite. At omega is equal to 0, all the magnitudes are infinity. And if you see angle 90, this is angle is minus 90 degree for all. If you will see omega is equal to infinity, is 0, is 0 for all. Okay, and if you will see angle is nothing but 1 2 3 3 into 9 270. Okay, so now these are what? These are the magnitude and angle. Okay, so now we are mapping this on GHS plane. Okay, so through Nyquist plot. Okay, so then we will understand this gain margin and phase margin simultaneously through the Nyquist plot. See, so this we have drawn. Okay, this is G1 of S, G2 of S, G3 of S. Numerator is different. Numerator is varying. Okay, so but denominator is same. So that's why the angle is same. But angle and magnitude all are same. But variation is different. Variation is different because of this and this gain. This factor is varying. So due to this, the curve will vary. Okay. So curve on the Nyquist plot will vary. So that we will see here. Now see, this is very important here. So now we are going to draw what Nyquist plot. So this is my Nyquist plot, and this is like this is my g of s, h of s, g of s, h of s plane. Yes, plane. Okay, so now now if you see, this is my origin, and here just I am drawing one unit circle. Let's say this is my unit circle. Okay, so this is my unit circle. So let me make this by red color. If red color is there is no red color at all. Okay, so no problem. So this is my unit circle. Okay, so now as we have what, as we have seen system, first one system m1, for m1, for m1, as we have seen, as we have seen what, at omega is equal to 0 magnitude is infinity. Okay, at omega is equal to 0 magnitude is infinity, at omega is equal to infinity magnitude is 0, 0. So this is like, it is passing like this. Okay, so this is, so let's say this is it's passing through this and this. Okay, so this is for my m1, m1. Yes, g1 of s system. So now, and this is what, cutting where, cutting where, this is always cutting at, this is my omega p1, this is phase crossover frequency, omega pc1, this is my omega pc1. So this is for, if you see, as we have seen, g1 of s is equal to what, 2 divided by s into s plus 1, s plus 2, s plus 2, and next is what, g2 of s is equal to, 12, 12 s into s plus 1, s plus 2, s plus 2, and here g3 of s is equal to, 24 divided by s into s plus 1 into s plus 2. Yes, now let let us draw for this second system. Here also we have seen what magnitude. We are getting what magnitude, infinity, and 0 at omega. At omega is equal to what? 0 and infinity. Yes, for all the system. For all the system. And here angle we are getting, angle we are getting at omega, this angle phi is equal to mm, minus 90 degree and minus 270 degree. Yes, this we are getting at omega is equal to 0, and this we are getting at omega is equal to infinity. Yes, omega is equal to infinity. So this is what, now this we have drawn for this system 1, g1 of s, and for second system we are going to draw this, and this will come like this, and it will pass through this unit circle exactly, and it will become like this. Yes, this is for system second. This is for system 1, g1 of s, and this is for g2 of s. Yes, this is for g2 of s. Now for g3 of s, if you will see, for g3 of s, this graph is like this. Yes, now we have drawn for all the system. So it is starting from where, it is starting from omega is equal to, 0. Yes, omega is equal to 0, and it is ending at what, omega is equal to infinity, omega is equal to infinity. Okay, so now this is for which system, g3 of s, g3 of S, and this is for G2 of S, and this is for G1 of S. Yes, and this is our what, unity circle. So this is my -1 and this is my +1. Okay, unit circle. This is my unit circle. Unit circle. Okay, so now what we can understand here, this is my omega PC because real axis. Okay, the plot will cut the real axis at what, phase crossover frequency. Phase crossover frequency. This is my omega PC1 and this is my omega PC2. Omega PC, omega PC2. Yes, and this is my omega PC. This is here omega PC, omega PC 3, omega PC 3. Yes, this is phase crossover frequency. Phase crossover frequency, the frequency at which the angle will become 180 degree, and this is my plus minus 180 degree line. Yes, okay, so 180 degree line, and this is my 90 degree and minus 270 degree line, and this is my 360 degree and 0 degree line, and this is my 270 degree and 270 degree and minus 90 degree line. Yes, so this is what, this we have drawn for all these three system here. Okay, three system here, because the denominator is same for all the system. Okay, so which is a function of S, so therefore the angle is same, and but the numerator, that is varying. Okay, numerator is, there is a variation in the numerator, so that's why there is a variation in this graph. Okay, so this first system, the graph is inside the unit circle, and the plot is what, plot is passing through, inside the passing through inside the this inside this unit circle. And if you will see, this next plot is passing just what, at the unit circle, it is cutting. Okay, so first plot is cutting the unit circle somewhere here. Okay, so and it is, and here if you will see, this is cutting unit circle here, and this third system is cutting, this third system is exiting this unit circle. Yes, unit circle. This is my omega PC. At real axis, we are always getting what, omega PC, phase crossover frequency. Okay, so in unit circle, so if you will see the this intersection point at omega, this unit circle, here we will get what, we will get omega gc, gain crossover frequency. Phase crossover frequency, as we know very well, phase crossover frequency, the frequency at which the angle is what, minus 180 degree. Gain crossover frequency, the frequency at which gain is what, unity. Gain is unity. So gain is unity. See here, this is my gain unity, means what is this? This is my omega gc 1. Omega gc1, gain crossover frequency, the frequency at which gain is unity. Gain is unity. Similarly here next plot, this is cutting what, unit circle. Here this is my omega gc2, so which means this is equal to omega gc2. So both phase crossover frequency and gain crossover frequency are equal. This means what? This means the system is marginally stable. Marginally stable. So now here, if you will see here what I am getting, omega gc. So this is what, omega gc 3. So this is my omega gc 3. Omega gc 3. This is my omega gc3, gain crossover frequency. Gain crossover frequency, which is cutting the unit circle at this point. Okay, so this point. So because as per definition we know very well, omega pc, phase crossover frequency, are those frequency at which the angle is minus 180 degree. Okay, so phase crossover frequency is what? Phase crossover frequency are those frequency at which gain is unity. If you see here gain unity, you see here gain unity, here you see gain unity. So this is what gain crossover frequency. Whatever the plot is cutting unit circle, that is over gain crossover frequency. Whatever the plot plot is cutting real axis, that is my phase crossover frequency. Phase crossover frequency. So plot so the plot which will cut the real axis, okay, so that point is nothing but phase crossover frequency. If the plot is cutting unit circle, that point is nothing but gain crossover frequency. Okay, gain crossover frequency. So gain crossover, or you can say that gain crossover frequency is the point where the plot cut the unit circle. Okay, what is gain crossover frequency? Gain crossover frequency is the frequency at which the magnitude become unity. Okay, so magnitude means gain, magnitude of the gain become unity. Okay, so that is what gain crossover frequency, or you can say the gain crossover frequency is the point where the plot cut the unit circle. Where plot cut the unit circle, here also where plot is cutting the unit circle, that is nothing but gain crossover frequency. Gain crossover frequency. Okay, what is phase crossover frequency? The frequency, in simple definition, the frequency at which the angle of the system will become minus 180 degree, or other way you can say that the phase crossover frequency is the frequency where the plot cut the real axis, where the plot is cutting the real axis. What plot? Nyquist plot of the system is cutting the real axis. That point is nothing but phase crossover frequency. Phase crossover frequency. By that way, you can make the definition. Okay, so that is understood. So now see we will see which one is stable, which one is unstable. As we know very well, whatever the plot that is cutting the circle, that is cutting the real axis inside the circle. Okay, inside the circle, whatever the plot that is cutting the real axis inside the circle, that all the system are stable. From here you can say which one is stable, which one is unstable. See here, this one is cutting what this plot is cutting real axis inside the unit circle. So that's why this g1 of s is what, this g1 of s, then we can say that g1 of s system is what, stable. So this is my stable system perfectly. This is my stable system. And if you see, this is frequency, what this curve is, what frequency variation. Okay, so this is the frequency variation, low frequency to high frequency, low frequency to high frequency. First frequency is coming omega gc1. Okay, so then omega pc1. This means what? Omega pc1 is greater than omega gc1, because first frequency is coming, which one is coming first? Omega gc1. So it is smaller because it is varying, okay, from 0 to infinity. First is coming omega gc1, then bigger is coming omega pc1. Which is bigger? Omega pc1. So that's why omega pc1 is greater than omega gc1. This means the system is what? Stable. And also you are seeing that this curve is what, this plot is cutting the real axis inside the unit circle. So that is the system is what? Stable. System is stable. Next is what? G. Next system is what? G2 of S. G2 of S. Now see G2 of S. So this is very where it is cutting the unit circle. That is my omega GC1. Okay. So omega GC1, and where it is cutting the real axis, that is my omega PC2. See here, both frequency. Okay. So here both frequency are same. Why? Because the plot is cutting the real axis and unit circle at the same point. At the same point. Okay. So that is what system. Or you can say that what is the marginal stability. Okay. So what is the condition for marginal stability system? Condition for the system to become words of stability or marginally stable is that when the Nyquist plot of the system when the Nyquist plot of the system cut the real axis and unit circle at the same point. What you can say that what you can say that when the Nyquist plot what when the Nyquist plot of the system, okay, when the Nyquist plot of the system cut the when the Nyquist plot of the system cut the unit circle as well as the real axis at the same point, then we can say that the given system is marginally stable system. As you are seeing here, this is my curve. Okay, so this next curve, this one. Okay, so this one, if you see this one plot belong to what system 2 means system 2. For system 2, if you see, for system 2, this plot is what this Nyquist plot is cutting what this is cutting what this unit circle and this real axis at the same point. Then I can say that this system is what marginally stable system for which, okay, so therefore I can say that this G2 of S is what? G2 of S is marginally stable system. Yes, this is my marginal stability. Yes, this is my marginal. This system is marginally stable system. For which omega GC2 is equal to omega PC2. Omega PC2. Yes, omega PC2. So just wait. So I can write this upside here. Okay, so this is what G2 of S. G2 of S is what? G2 of S is marginal stable. Okay, marginally stable. Marginally. Marginally stable. Stable. Okay, marginally stable, for which omega GC2 is equal to omega PC2. Omega PC2, because it is cutting both unit circle and the real axis on the same point. Now coming to system 3. System 3 plot is what? This one, outer plot, this Nyquist plot. Okay, if you see, this third plot is belong to what? Belong to third system. Okay, so for third system, if you see, for third system, if you will see this third system, which is cutting the unit circle here, and which is cutting the real axis what? Beyond the unit circle. Okay, beyond the unit circle. Okay, so the system for which the Nyquist plot cut the real axis beyond the unit circle will become unstable. How you can say that? When the system is unstable when the Nyquist plot of the system cut the real axis beyond the unit circle, that system is unstable system. How you can say that? Because if you will see, this is what? Variation of the frequency. Yes, this curve is nothing but variation in the frequency. Yes, here omega is what? Here omega is what? 0 to infinity. Which one is coming first? Omega PC1. This means this is less. This is which one is coming after? Omega GC3, because omega GC3. So this means what? Omega GC3 is greater than omega PC3. So from here we can say that this system G3 of S, G3 of system is nothing but it is unstable system. Okay, so By visualizing this graph properly, you can say, because this curve automatically you are seeing that this is what unit circle, and this curve is what cutting the real axis beyond this what, beyond this unit circle, and hence you can see that. So one way of seeing the instability of this system is this way. Okay, so this is the one way, and other way is just seeing the frequency, which one frequency is greater, omega gc3. Okay, so this is what unstable, and for which omega gc3 is greater than omega pc3. So this is what unstable system. Okay, and it is cutting what, it is cutting the real axis beyond the unit circle. So this is all about what, this is all about stability of the system. Okay, so what is gain margin? Gain margin is nothing but, just see this, gain margin is nothing but how much distance bit. So distance from what, origin, distance from origin to what, origin to the real axis, where the plot is cutting, the real axis. Okay, real axis. Let's say this is my m1, this is my m1 distance. Okay, and let's say, and this is my unity distance, as you know very well, this is my unity distance, and this is my, let's say this is my m2 distance, yes, m2 distance, this is my unity distance. And from here I can say that what, m2, if you see m2 is what, m2 is greater than m1, m2 is greater than m1, and m1 is what, you can see here from m2 is what, m2 is greater than unity, and m1 is less than unity, yes. This is nothing but m3. Okay, you can say m3 is greater than unity, m1 is less than unity, and here m2 is equal to what, unity, is equal to unity. So this is what, greater than unity means it is unstable, yes, it is unstable. And m1 less than 1 means, it is stable. m2 is equal to 1 means it is marginally stable. This one is marginally stable, you can say. Okay, so now you can check it from here. Okay, check it from here, and this is my magnitude. And gain margin, how you can write the gain margin, then after that how you can write gain margin and phase margin. So if you will see for gain margin, gain margin is nothing but 1 by reciprocal of this magnitude, reciprocal of this distance, This is for gain margin for system 1, and gain margin for system 2 is what, 1 by m2, where m2 is what, just 1. So this is what, 1, and this is what, 1 in linear, and it is 0 in dB. So gain margin 3 is nothing but reciprocal of m 1 by m3, what is 1 by m3? If you see, this is what, 1 by m3. Okay, so gain margin. So this is what, linear. If you see m3 is what, m3 is greater than unity, greater than unity, and definitely this gain margin will come less than what, less than 1, and it in dB it will go in negative. This means what, gain margin here. If you see gain margin 3 is less than 0 dB, because it will go below the 0 dB, because it will come negative. Why? Because m3 is what, greater than 1. M3 greater than 1 means 1 by something is greater than 1, it will come in less than 1. Less than 1 means it is negative in dB. Yes, this means what, system is unstable. So here it is 0 dB. Here M1 if you see M1 is less than 1. Less than 1 means gain margin M1 will come greater than. greater than what? Greater than 1. Greater than 1 means dv. In dv it is positive, it is positive. So hence from here you can say that gain margin m1 is greater than 0 db, greater than 0 dB, so that this system is stable, and this system is equal to gain margin for system 2 is what? 0 dB. So it is what? It is marginally stable and it is unstable. Okay. So this is about gain margin. If we see for phase margin, see phase margin. Phase margin is nothing but just you draw this. You draw the straight line from origin to the point where the curve is cutting the unit circle. Curve is cutting this unit circle here. So this means what? If you will draw this straight line here, and just now after that you just calculate this angle. Okay, so this angle, let's say this is my angle phi. This is my angle phi m1 for system 1, for system 1. Okay, so now I want what? I want to reach this 180 degree, 180 degree. Okay, so 180 degree. So I want to reach up to this 180 degree. So let's say this is my angle. If you see, phase margin. So this angle is let's say 1 minus 120 degree. Okay, minus 120 degree, and if you will see 120 degree. Okay, so then what is the phase margin for this? Phase margin is nothing but 180 degree plus angle. So this is my angle at what? Omega gc. Okay, omega gc, this angle is what? At omega gc. So phase margin equal to 180 degree plus omega gc, angle at omega gc, which is nothing but 180 degree minus 120 degree is nothing but 60 degree. 60 degree. So this is what 60 degree. If I will jump to 60 degree, I will reach to what? 180 degree. Okay, I will reach to 180 degree, and here the phase margin is what? Phase margin is nothing but 60 degree. 60 degree of phase margin. Yes, 60 degree of phase margin is there. Yes, similarly for this next one, this is what? If you will draw this angle from here to here, next where it is cutting just this point. Yes, up to this point. So this is nothing but 180 degree. So this next curve, if you will see this next curve, it is cutting where? It is, I am not drawing this line, otherwise it will get mess. Okay, so I don't want to make any mess about this. So just see this, where it is cutting here, 180 degree. So it is what my 180 degree. 180 degree minus 180 degree is what? 0. So phase margin is here is what? 0 degree. Phase margin 0 degree means it is marginally stable. Here phase margin greater than 0 means it is stable. It is what? Stable. But it is marginally stable. And see here, so see here, this angle where it is cutting here, just draw the line here, from here. So origin to that distance, draw this, and after that calculate the angle from this. Okay, so this is greater than 180 degree. It is coming greater than 180 degree or not? Yes, if you will count this, if you will count the angle from here to here, up to this angle. Okay, so up to this is 180 degree. Then after that, this is greater than 180 degree. Okay, so what is phase margin? Phase margin is nothing but 180 degree angle omega gc. So angle omega gc. Okay, but this angle omega gc is how much? It is greater than 180 degree, and definitely here the phase margin is coming what? Phase margin is coming negative. Yes, negative. So therefore the phase margin coming negative means this system is unstable. This system is unstable because this system is unstable, because phase margin is negative. Okay, so this is all about phase margin and gain margin, how to check from this unit circle, from this Nyquist plot. Okay, so that's all about today, about gain margin and phase margin. Okay, so thank you very much to support my lecture. Okay, so thanks a lot. Okay, bye bye. Okay.